This is a lesson on systems of nonlinear functions in a Precalculus course. I'm introducing this in the Quadratics unit. We may see higher powers, but I wanted to introduce it in the Quadratics. We have seen intersections in systems with linear equations. This is a review. You can go back and look at the lecture if you'd like to review that. But what we're doing is overall we're algebraically solving for the intersection between two functions, and we're observing it on the graph as well, right? Our algebraic solutions should correspond to our graphical solutions. And so we're going to set up a system of functions in order to solve, but we're going to do this with nonlinear equations. I have an example there. You can see that I have a line. This is definitely a line, but this is definitely not a line. This is not a line, and so that just qualifies it as nonlinear. Turns out this is a parabola, because this is a quadratics unit, so I have it as a parabola. So what we're going to do is algebraically solve for the intersection of two functions given their equations and use a graph to verify. We're going to write equations for functions given a graph. You should be able to do this. If you're given a graph, can you write equations for functions and then solve for that intersection? And set up a system of nonlinear functions in word problems, all right? So let's do this example here real quick, just a quick example. Algebraically solve for the intersection. Okay, so we have a line, and this is an inverse function, but we're going to use substitution. It says use substitution. So we're using familiar strategies of algebra that we've learned in this class or before this class, wherever I had them before. It says use substitution. So wherever I see y in the other equation, I'm going to put in x plus 2. I'm just going to do a substitution in there. So x times x plus 2 equals 3. We're going to solve. I'm going to distribute x squared plus 2x. I'm going to move the 3 over and get the quadratic form. General quadratic form. You may notice that this factors. I'm going to have an x plus 3 and an x minus 1 equals 0. And using the zero product property, I can set up and solve for two values of x equals -3 or x equals 1. And this will be the solution. I expect this two solutions because I end up with sort of a quadratic in here. There should be two intersection points. And I can check, of course, you already know how to check, is with a graph. Let's check this graph out here. This may look like something you've never seen before. Definitely you recognize the line, but you might not recognize the inverse function. So here's an inverse function here. And it is an odd function. If I flip it this way and then this way, you can see I get the same function back again. It's an odd function. So it has some values here down in the third quadrant. It's a first quadrant, third quadrant function. And so it's going to intersect that line. That line's going to intersect those two in each of those quadrants. And so that's what we see, is that there's an intersection at -3 and there's an intersection at +1. Okay, so that's how to solve. We're going to use, like I said, familiar strategies for solving algebraically as we've seen in our classes before. Okay, this example here is an intersection. You may see that it's an intersection of two parabolas. Do you see two parabolas there? Two quadratics. We have two quadratics, the power of 2 there. It says use algebra to find all solutions of the system. And it may be a knee-jerk sort of thing, like you want to solve for y and plug it into the x squared into the other, and then you'll have like squared terms running around. But the easiest way to do this is to note that these are both to the first power, or have a coefficient of 1 out front. And if I multiply, let's say, the top equation by a negative sign, if I take that negative sign and I distribute it all the way through, I'll have a -x squared, a +2y, and a -17. And then I can just add these two and use the strategy of elimination, right? So I get 7y. 45 minus 17 is 28, and I get y equals 4. Okay, so I got a solution really quick here. It looks complicated, two parabolas intersecting, crazy, right? And it seems like maybe parabolas could intersect never. right? If they're on two different parts of the graph, they may intersect never. It seems like maybe they could intersect at one point. There's two parabolas. They intersect at one point, right? They're not going to maybe intersect any more than that. And then the other way that parabolas can intersect is they may intersect at 2 points. We could see that maybe those two parabolas intersect. What's going on here, right? So overall, what I'm going to notice when I do this, I have a y equals 4. That doesn't tell me the x values. I still need to solve for the x values. So let's use one of these equations, x squared minus 2y equals 17, and we're going to solve for x. We're going to plug the 4 into where the y is and solve for x. So x squared equals 17 plus 8, which is 25. So I get x equals the square root plus or minus the square root of 25, which is plus or minus 5. So I'm going to see that there's two intersection points between these parabolas. I'm going to have a negative 5, 4, and I'm going to have a plus 5, 4. Right? These are the x values. There's two of them. And it happens to be the same y value for both of them. So let's check out the graph. Let's see how we did here. So there's those two parabolas. They're nice, even functions. They're nicely symmetrical about that y-axis. And we can see that they're intersecting at 2 points, like I had predicted. One's a facing up parabola, one's a facing down parabola, and they're going to intersect right there at those 2 points. Notice that there's a negative 5 and a positive 5, and 4 is the y value for them. So a pretty clever way to solve there with elimination. Make sure you're checking your solution with your graph. The next thing I wanted to move on to during this lesson is inequalities. And we've looked at inequalities with linear functions. All right. We just looked at inequalities, just simple inequalities, and we looked at compound inequalities where there's a region of overlap, right? So that's where I'm going with quadratic functions is can you do just a simple graph a parabola and identify a simple inequality? So simple inequality, I just have, here's a line. We did that with the linear, right? But here's a quadratic. Here's that parabola. When is y less than that parabola? So what I'm going to note, that's all that blue area up here. I don't know if that's a little confusing to you because I put the line on at the same time. But this one here is the blue shaded portion in here. All of these values of y is less than that parabola. Okay. We can do a compound inequality. I did the compound inequality between the line and that parabola. The line is when is the output greater than the line? Well, that's where all this red area is. That's that red area. And if we wanted to do a compound inequality, we'd have to take both of those together. We're going to have to ask where is it red and blue? Where is it red and blue? And when I look at that, there's an area right here where it's red and blue, and there's an area right here where it's red and blue. So what I would need to do is identify those regions, right? And you may see it here. Where does that start? There's an intersection point here and an intersection point here. Okay, so it's going to be in this region all the way to a negative infinity, and it's going to be in this region to a positive infinity, but I'd have to identify those values in there. And I could identify those values in there. We did that in the previous section. I would have I would just set them equal, right? Because if we want an intersection, we have to set them equal. So I would say negative x plus 10 has to equal x squared minus 4x plus 10. And that would give me, if I solve, that would give me those two intersection points for which to set my domain for this solution, right? Plus 10 cancels on both sides. I'm just doing this because it seems kind of easy to do. X squared plus 5x equals 0. Is that true? Did I add and subtract correctly? No, I didn't. This should be minus 3x equals 0. Those 10's canceled. I add a plus x on both sides, and I get a minus 3x, right? So I see that this factors x and x minus 3, so that gives me x equals 0 and x equals 3, and we can see that's true on the graph. X equals 0, x equals 3. So if I wrote the solution to this guy, it would be a union of two areas from negative infinity all the way up to 0. And then in that region in there between 0 and 3, there's no overlap between the red and the blue. And then I would union it with, and I want to put a bracket on the end because it seems like it can equal that value, can it? No, it can't equal. I think that's where I get a little confused in here. It can't equal it because the line can't be equal, right? The line is a dotted line there. And so I'll put a parenthesis there, and then it goes 3 all the way up to infinity. So that would be the solution for this compound inequality. All right. So you're going to be doing some examples of that. Solving quadratics, that's going to be a key skill, and then also doing inequalities. Let's do a quick simple inequality here that I see students have trouble with. It says solve when the inequality, when the function is less than or equal to 0. And they give the graph. I think you could write down the function, right? I see that it's moved over 2 and up 4, left 2 and up 4, so that'll give me a general form, x plus 2 squared plus 4 for my function. And you may be ambitious to like solve for that value. And I think if you wanted to, you should be able to solve for that value. We can solve for our a value by just plugging in a point. But what I'm going to note, and why I think this problem is hard, I think this is the simplest thing. It says, when is the function less than 0? So I'm going to look at the graph and say, when is this red line below the x-axis? And I can see the red line is below the x-axis here and below the x-axis here, extending to negative infinity and positive infinity both directions. So when I look at the solution here, and I think that's when what students get confused about, is they're not sure what it's asking. They're just asking, when is this graph in the negative value of y? When is that? And so you would say it's from negative infinity all the way up to 4. And I think that is a square bracket there because it can equal 4. And then it'll be a union with, in this region it's positive, in these regions it's negative. So this is maybe a behaviors of graph skill. And then it'll be a union from 0 all the way up to positive infinity for when it goes back down into the negative, right? It keeps going and going and going to positive infinity. So that would be the answer to that problem. I don't think it's terrible, but it may be a little elusive, like to correlate what they're asking and the information given on the graph. Let's do a little bit more rigorous inequality here. It says solve the inequality. Okay. We recognize that as a parabolic, a quadratic, right? And we recognize what we need to do in order to solve. I have a positive one out front. I'm going to leave that positive, my squared term positive, so I'm going to have m squared. I'm going to move these two over, so I'm going to get plus 20m plus 96. And I didn't do any division or multiplication, so I don't need to change the direction of my inequality sign. And now I have nothing over on that side, right? So this is the form that we like to solve. And you could use a quadratic formula on this, negative 20 plus or minus the square root, blah, blah, blah. But what I'm going to notice here, and maybe you notice it, 96, the factors of 96, I like it because it's a factor of 12 thing. If you know factors of 12, you're going to get m plus 12. And 8 times 12 is 96. And when we look at that, that is 20. So I have this going on. What I'm doing is I'm finding where these two functions independently meet is what I'm doing. So the way I like to think about it is f of x is m squared, and g of x is negative 20m minus 96. So we have a parabola and we have a line. And we want to know, where does that parabola intersect that line? What are those 2 points? Well, when I set them equal, right, or it says I'm finding the intersection, so I would set them equal. So I guess maybe that's what I'll do here, is I can set this, make this an equal sign, right? And that will let me find the intersection points. Overall, what it's asking is, when is f of x less than g of x? When is that true? When is the parabola less than the line? When is the parabola less than the line? All right, and I don't know those intersection points, but I am going to notice that it's going to be in this region from here to here. That's when the parabola dips below the value of that line. That's where the parabola is less than the line. And so when I solve, I get m equals negative 12, right? Zero product property, or m equals negative 8. Those are those two values. So I'm going to see that this is a negative 12 and this is a negative 8. I know I haven't drawn the graph yet. You may be curious why I'm so confident. Well, I know this is an upward facing parabola, right? It's upward facing. It's the simplest parabola ever. It's just centered at the origin and faces upward, and it doesn't have any scaling. This is a line with a negative slope, and it crosses the y-intercept at negative 96. Okay. So let's look at the graph. Let's look at the graph. I'm going to guess that this is in this region here. Let me pull this up. Boop. So as we look at this graph, okay, so it does have an intercept at negative 96, but so it intersects this parabola over on the second quadrant, right? If I think about the quadrants of a coordinate system, and I have, what is this? Negative 8 and negative 12. And we can see that in this region in here, you can see that's where the parabola falls below that line. It's right in this region right in here. It's not highlighted. You can't see it very well on this graph, but on my original drawing you could see that it was that way. So that's how you would solve a more rigorous quad inequality. One thing I see as a strategy in here that I'm going to remind you of before even looking at a graph, right? It may be, and I see this strategy, I have 3 different regions, and what I want to do is check in the 3 different regions what the inequality is, right? So I would have a region where m is less than negative 12. I would have a region between negative 12 and 8, negative 8, and I would have a region greater than negative 8. Do you all see that? And so then I can do this algebraic test. If I couldn't look at the graph, I would do an algebraic test here to say, where is it negative? I think that would be the easiest way to do that, is where is this negative? If I plug values into this equation, if it is negative, then it's true. If it's positive, it's false, right? Because I want this less than negative, or less than 0, all right? So if I plug in, let's say I plug in negative 20, I get 400 minus 400 plus 96. What is that, 96? This is a positive value, so that would be a false situation. I want it less than 0, and if it's positive, then it's not. In between, let's choose negative 10. Negative 10 is in between there. It's a nice number. So I'll get 100 minus 200 plus 96. 196 minus 200 is a negative 4. I get a negative number, so this is a true statement. And then let's plug in something easy. 0 is greater than negative 8. 0 plus 0 plus 96, right? 0 plus 0 plus 96. This gives a positive 96, so this gives a positive value, so I have a false here. So your teacher may have had you solve algebraically before and do this test in different regions to figure out where the inequality is true. It's true only in this region. We already knew it. If I did this, I want a less than sign, so I'm going to have parentheses on the end, and I would go from -12 to -8. Make sure you're ordering these from least to greatest, and -12 is less than -8. So hopefully that helps you on a problem like this in the future, and that you enjoy doing inequalities and intersections with quadratics.